Hello everyone, welcome back to Introduction to Logic. This week we're going to continue with natural deduction. Specifically, we're going to be walking through some proofs. So we're going to be putting into practice all of those rules that we learned in the last 2 weeks. All right, so let's get right into it. There are a few different proof strategies that you can employ. In our book, For All X, they talk about working forwards, working backwards, and trying to prove indirectly. So we'll try to get some examples of each of those things today. Let's first remind ourselves of the rules that we do have, right? So we have reiteration, which allows you to just repeat something that you already know. We have conjunction elimination and conjunction introduction. We have conditional elimination, conditional introduction, disjunction elimination, disjunction introduction, negation elimination, negation introduction, biconditional elimination, biconditional introduction, indirect proof, and explosion. These are all of our rules for right now. Next week we will learn a couple more rules, but those rules aren't strictly speaking necessary. They just make your life a lot easier. To get an idea of what I mean, for example, if you have this premise, if P then Q, and you know that Q is false, well, it follows that P must also be false. We can prove this using the rules that we have up above. We don't need anything in addition to what we have here, but it's going to take a few steps. We're going to have to make some assumptions, and it's maybe not immediately intuitive to you how you should go about doing that. Next week, we're going to learn a rule that will allow us to do that in one move, right? So it's the rules that we're going to learn next week just allow you to achieve the same things we can already, but faster. All right. So now that we have our rules here, let's do some example proofs. Let's start with this. Premise 1, if P, then Q. Premise 2, if P, then R. Premise 3 is P, and we want to prove Q and R. Okay, so before we even get started with proof strategy, we have to get our lines. Okay, and let's get our premises down. 1, if P, then Q. 2, if P, then R, and 3, P. Okay, so when you are approaching an argument like this and you want to prove it, what I would recommend doing is starting by examining your conclusion, right? What kind of proposition is your conclusion? I notice that my proposition is a conjunction, okay? And, right? So this says Q and R. Further, I know that because it's a conjunction, the only way that it's true is if both sides of it are true, right? Q and R both have to be true. Okay, so how does that help me? Well, it tells me that if I can establish that Q and R are true, I can get this pretty easily by using conjunction introduction, okay? So in effect, what I'm doing here is I'm working backwards. I'm saying, well, I know I want to prove this, Q and R, so I'm just going to write it at the bottom, right? I want to prove Q and R. And I know that in order to do that, I first need to get Q on some line, and I need to get R on some line by themselves. Then I can join them together with conjunction introduction. So this is going to be my strategy. This is what I want to do. Now the task becomes, okay, well, how do I do this? How do I get Q and how do I get R? For that, we're going to need to look at our premises. Okay, looking at my premises, is there any straightforward way of getting Q and getting R? So let's go to the premises and look and see where Q and R occur. Well, I have Q here and I have R here. And notice that they're both consequence of conditionals, right? They're both attached to a conditional. Well, because they're the right side of a conditional, the consequent, it means I can unlock them. I can get them out of that conditional so long as I have the key, right? The left side here. I need to find P, and I do have P. So that tells me I will be able to get them out of that conditional, and I'm going to want to use conditional elimination to do that. So here's what this proof is going to end up looking like. On line 4, I'm going to derive Q, and I'm going to say conditional elimination from 1 and 3. On line 5, I'm going to get R using conditional elimination from line 2 and 3. And then at the very end here, I can join these two things together. Conjunction introduction 4 and 5. And that's it. So this is a fairly simple proof, but the idea here is that once you analyze your conclusion, you see what it takes in order to generate it. It is sometimes possible to work backwards this way, right? All right, let's do some more. See if I can delete this and preserve the lines. Another fairly simple one. Suppose we know P and Q, and we want to prove P or R. Again, let's start by analyzing our conclusion here. P or R. Well, I notice that it's a disjunction. Okay, the first thing you should do is look and see, well, what kind of sentence is it? It's a disjunction. Now, what does it take for a disjunction to be true? One of these sides needs to be true or both. One of these sides or both. I know that because of that, and because of disjunction introduction, if I can establish that just one side of this disjunction is true, I can get P or R, right? So what I'm going to be doing then, what I expect, is to derive P or R using disjunction introduction after having found just P or just R by themselves. Now, can I get just P or R by themselves? Well, yeah. P is part of a conjunction here. And you can always break apart a conjunction because a conjunction is telling us both of these things are true. So my premise is P and Q. On line 2, I'm going to break the conjunction apart using conjunction elimination from line 1. And then very simply, I can get P or R, disjunction introduction, line 2. Yeah, not too bad. All right, let's start to build in some more complexity here. Okay. Suppose we know that P or Q. We know that if P, then R. If Q, then R. And we want to prove that R. Okay, so let's start by getting our premises out here. P or Q. If P, then R. If Q, then R. All right, so let's start the same way. Let's analyze our conclusion. Oh, well, there are no connectives here. There's just R. Okay, so how do I work backwards with just R? Right? There's no inferences to draw about the nature of my conclusion. It's just a sentence letter. Well, you can't really. Now we are forced to work forwards. Working forwards just means to use our inference rules over our premises until we get information that's useful to us, information that might bring about our conclusion. Okay, so what I personally would advise that you do in a situation like this where it's not clear, like, I'm trying to prove that a conjunction is true, thus I need to prove both sides, etc. When it's not clear what to do, look at your conclusion, R, and try to find it in your premises as like a component of some other sentence. I see in premise 2, it's part of a conditional. And the same for premise 3. It's the consequent of 2 conditionals, which again means that we could unlock it. And that would be perfect. If we could unlock it from either of those conditionals, that would be enough to prove that our conclusion must follow from the premises. But in order to unlock it, I need the key, right? I need that antecedent on the left side, P or Q. So the question now is, do I have those? Do I have either P or Q? I don't have them on individual lines, but I do have this disjunction. This disjunction says that one of those two, if not both, must be true. So what I'm going to need to do is make that disjunction useful. And the only way to do that is use disjunction elimination. So I know that's going to be my strategy. I want to use disjunction elimination so that I can use conditional elimination to unlock R from these two things, these two conditionals here, right? That's going to be my strategy. This is what it looks like. In order to use disjunction elimination, I have to make more assumptions. So I'm going to need more bars. This first assumption is just going to be P. Why P? Because it's the left side. It's the left side of the disjunction that I'm trying to eliminate. Okay? You start with the left side first, and then we'll assume the right side later. Having assumed P, can I get to R? Yeah, absolutely. I can get R from conditional elimination. This is 2 and 4. Always cite the conditional first, then the antecedent. That's all that I need from my assumption of P. So I'm going to shorten the bar here. Now I'm going to begin my assumption of the right side. Get another bar. Okay, I'm going to assume Q because it's the right side of my disjunction. Having assumed Q, I can get R using the same thing. That's going to be 3 and 6. Okay. Line 3 is where I have my conditional. Line 6 is where I had the left side of that conditional. Great. So now I can say, since both the left side and the right side of that disjunction on line 1 led me to the exact same result, I can eliminate that disjunction. The way we do this, we cite the disjunction, and then we cite both subproofs, 6 through 7. And that's it. I have R. Okay? So in this case, we were forced to work forwards to see how we can transform our premises into something that might be more useful to getting the conclusion. Let's do some more. Okay, there we go. How about this? If P, then Q. If Q, then R. Thus, if P, then R. Okay, so what we're doing here is trying to prove that conditionals are transitive. They are. This is valid. Now we just need to prove that it's the case. Let's get these numbers out of here because they're no longer going to work. Let's get our premises first, and then we'll talk about proof strategy. If P, then Q. If Q, then R. Great. All right. Let's start once again by analyzing our conclusion. If P, then R. Well, this time there is a connective, right? This is a conditional, okay? So couple things here. When you have a conditional as a conclusion, what I would advise you do first is look in your premises and see if you have the entire conditional somewhere, right? Because it might be as simple as this. Suppose you had the following premise: P and if Q, then R, and your conclusion is if Q, then R. Okay, well, this is pretty straightforward. All you need to do is use conjunction elimination to get if Q, then R. No big deal. You don't have to worry about it being unconditional at all. So what I would advise you do first when you have a conditional as a conclusion is look and see if it appears in the premises somewhere. If so, consider working forwards. Okay, consider working forwards, transforming all the information in your premises until you get something more useful. Okay, in this case, we do not have if P then R, right? We don't have that. So that's not going to be available to us. So we're going to be forced then to work forwards. But with a conditional, there's a special sort of strategy for this. With a conditional, if it's a new one, it doesn't appear in your premises, what we're going to do is start by assuming the left side and try to get to the right side. This is the strategy for conditional introduction. What we're doing is trying to introduce a new conditional. So I know I want to get if P then R. I know in order to do that, I need to begin by assuming P and arriving at R. Okay? These are things that I know just based on the fact that the conclusion is a conditional. I'm going to draw my assumption bars here. Okay. We'll call this 3. So, having assumed P, is there any way for me to get to R? This is where working forwards comes in. Well, I'm not sure about getting R, but I know I can get Q, right? I can get Q using conditional elimination, line 1 and 3. Okay. Now that I have Q, I see that, oh yeah, I can get R now, right? This is conditional elimination 2 and 4. And that's all that I wanted to do, right? Now that I have R, we're gonna have our line 6 all the way down here. I can do conditional introduction, and I'm going to cite the entire subproof. So that's 3 through 5. I've proven a new conditional. Okay. Not too bad. So conditionals are a bit of a special case. If you see a conditional as your conclusion, step 1, check to see if that exact sentence is part of your premises within some more complicated premise. Step 2, if it isn't, then start by assuming the left side of the conditional. Once you've assumed the left side of the conditional, start working with your premises and your assumption to see if you can get to the consequent, the right side. If you can, great, that's conditional introduction. Let's do a couple from the book. These are the practice exercises from chapter 17. We're just going to do like the first 3. Let me get rid of this stuff. Okay, let's look at, again, problems at the end of chapter 17, section A, number 1 to start. We have if A, then B, if A, then C, and we want to prove if A, then B and C. Let's get our premises down, and then we'll talk about strategy. If A, then B. If A, then C. And we're trying to prove if A, then B and C. Again, this is a conditional, right? We're back dealing with conditional. So, step 1, look to see if this entire thing appears in your premises. It doesn't, right? There are similar looking things. There's similar looking conditionals, but they're not the exact same. Okay. So that means we're not going to be able to transform our premises alone and get to our conclusion. We're going to need to make some kind of assumption. Since this is a conditional, we should start by assuming the left side. So let's do that. I'm going to assume A. Okay. Now that I've assumed A, I want to try to get to B and C. This is where I'm just sort of playing with our premises comes in. Obviously, it's best if you can form some kind of game plan before you just start trying to derive as much information as possible. But there is no wrong way, strictly speaking. If your proof ends up having 10 more steps than someone else's proof, so long as you got to the same result, the same conclusion, and you only used valid inference rules, the proof is good, right? We can talk about some proofs being more elegant than others, but elegancy is not the test, right? Okay, so I've assumed A. What can I do with it? Well, I can get B using conditional elimination 1 and 3. And I can get C using the same move, 2 and 3. Okay, does that help me at all? Well, what I'm trying to prove now that I've assumed the left side of this conditional is this, B and C. And I can see that is definitely going to help me, right? I can join those two things together, B and C, with conjunction introduction. 4, 5. And now that I've done that, that's all I was looking for. I assumed the left side, I got the right side, so I'm able to come outside of this assumption altogether, say if A, then B and C, conditional introduction, cite the entire subproof. Not too bad. Let's move on to problem 2. Yeah. Okay. Problem 2, if A and B, then C. Therefore, if A, then if B, then C. This is going to be an interesting one. We only have one premise. A and B, then C. Okay. So once again, we have a conditional as our conclusion. So check to see if this entire thing appears in your premises. It does not, right? Okay. So we're going to start with that same strategy. We're going to assume the left side, and we're going to try to derive the right side. So we're going to start by assuming A. Get our assumption bars down. Here we go. Now, having assumed A, is there anything I can do with my premises to derive the consequent? Well, notice that the consequent is another conditional. It's another conditional. So we're going to follow the same steps again. Does if B then C appear as a premise or as an element of a premise? No, it doesn't. Which means we're going to need to, again, assume the left side and try to get to the right side, okay? So I'm going to assume B under my assumption of A. This is a nested assumption. An assumption nested within another one. Okay, now that I've assumed B, is there anything I can do with my assumptions and my premise to get to C, right? My new goal is C. Well, yes, I see that in premise 1, I can derive C so long as I have the key here, A and B. And now that I've assumed both A and B, I can get that, right? A and B, conjunction introduction, 2, 3. Okay? You can bring any two lines together and put a conjunction symbol in between them. Now that I have A then B, I can get C using conditional elimination 1, 4. Now, that's all I wanted out of this, right? I wanted if B then C. I assumed B. I've now proved that C follows, which means I'm entitled to say if B then C, conditional introduction 3 through 5. Now, notice I'm no longer under the assumption bar of B. Whenever you use conditional introduction, you get rid of an assumption. We no longer have access to B. But I'm still under the assumption of A, which is exactly what I wanted. Let me make this shorter. Right. The conclusion required me to start by assuming A with the hopes of being able to derive this, which I just did. So now I get to do the same move. If A, then if B, then C. Conditional introduction, this time 2 through 6. Okay, so this might have seemed more difficult, but it's just using the same move again, right? It's just using this conditional introduction strategy within itself. Not that difficult with some practice. Okay, let's do one more from the book before we move on. This is problem 3. We, again, only have one premise. If A, then if B, then C. So our conclusion from last time is now our premise. And we want to prove that if A, then B, then if A, then C. Okay. Whoa. So we have a conditional as our conclusion. So step 1, look and see if this exact sentence appears in your premises. It does not, right? Those are pretty rare, but they do happen. All right, so let's get our premise down here. If A, then if B, then C. Given that it does not appear, our conclusion, in our premises, what are we going to have to do? We're going to have to start by assuming the left side of our main conditional. That's this. I'm going to assume if A, then B, right? So if A, then B. Okay. And I want to show that by assuming if A, then B, I can get to if A, then C. Okay? That's the goal. All right. Can I do that? With just my assumption and my premise, can I get to if A, then C? No, there's no clear, straightforward way of doing that. But do notice that once again, I'm trying to prove a conditional. So again, I'm going to use the same strategy. I'm going to start by assuming the left side here, A, right? This is going to be yet another nested conditional introduction. Okay, now that I've assumed A, my goal is to get to C. Okay. All right. First step along that process, I see that I can get a couple of different things, right? I can use my new assumption in premise 1 to get if B, then C, and I can use my new assumption and my old assumption on line 2 to get B. So I'm just going to go ahead and get both of those things. So I'm going to start here, if B, then C. That's conditional elimination 1 and 3. And then I'm going to go ahead and get B by itself as well. That's conditional elimination 2 and 3. And hey, would you look at that? Now that I have both of those things done, I can get C. Conditional elimination 4, 5. Okay, perfect. That's what I was looking for. Having assumed A, I can get to C. That allows me to come outside of that assumption to say if A, then C, conditional introduction 3 through 6. Now again, that's what I was looking for with my first assumption. So I get to come outside of that assumption bar now. Let's make this smaller. Wrong tool. To say, if you assume if A then B, then you can get if A then C using conditional introduction 2 through 7. Okay, not too bad. All right, so now going to work a few more of my own here. One more of a general kind of proof, and then we're going to look at a couple of what are called theorems. Okay, we'll talk about theorems in just a moment. First up, let's talk about that argument I gave you at the very beginning of the video. If P then Q, not Q, therefore not P. This is always valid. It's called modus tollens. Okay, modus tollens. But can we prove that it's valid? Yes. Let's do so. I'm going to put my premises down, then we'll talk about proof strategy. 1, if P then Q. 2, not Q. All right. So look at your conclusion. We have not P. Does that appear anywhere in the premises? No, it does not. Okay. When you have a single sentence letter like this, and it does not appear in the premises, your next step is to try to work forwards. Is there some way of unlocking it from the premises? And in this case, unfortunately, no. Look, there's nothing I can do with these two premises together right now. I don't have any proof rules that allow me to have these two premises interact. Okay, that means I'm going to have to make some kind of assumption. Nothing's giving, so I need to make an assumption to force something loose. Okay, what kind of assumption should I make? Well, when you have a case like this, always assume the opposite of your conclusion. Here, what we're trying to do is use a negation introduction or indirect proof. That's the strategy we're trying to take. As a reminder, both of those work by showing that a contradiction leads to the inverse of your assumption, right? So if you assume P and that leads you to a contradiction, you know that P must have been false. So what we're going to do now is assume P, that's the opposite of our conclusion, try to get to a contradiction. And if we do, we know that our assumption was false. Okay? This is called proving indirectly. All right? We're trying to prove indirectly here. I'm going to assume P. And it's pretty simple to prove modus tollens using this way, as you can probably see already. Now that I have P, I can get Q. That's conditional elimination 1, 3. And now that I have Q, I have a contradiction, right? Q and not Q do not go together. That's negation elimination. Technically, you're supposed to cite the line that has the negation on it first. That's 2, and then 4. Now, when you arrive at a contradiction, there are a couple things you can do, but the only one that's useful for us in this particular case is to end our assumption. Say, look, I arrived at a contradiction. That means my assumption must have been false, not P. This is negation introduction 3 through 5. Okay, so I mentioned there's a few other things you could have done with the contradiction just that they wouldn't be useful. Just so you don't make the mistake, let me show you what I mean. Suppose you got to the contradiction symbol and you go, hey, if I get a contradiction symbol, I know that I can get whatever I want using explosion, right? So why don't I just write not P, explosion 5? Well, the reason you wouldn't do this is because you're actually still under the assumption. You would still be under the assumption here. Explosion doesn't have the power to discharge or get rid of an assumption. Thus, you can't end the proof yet. You're not allowed to end a proof that is still under assumption other than the premises, right? So explosion's not going to help us here. You've got to use something like negation introduction, or indirect proof. The difference between those two just being the negation introduction puts a negation symbol in front of your conclusion. Indirect proof does not, right? So let's see. Get rid of this. Okay. Let's see. As an example of indirect proof, should we just run the same thing but negated? Let's see. And I'm trying not to use double negation rules. Conclusion would be not P. Okay, so this is valid. But again, we'd be introducing a negation. Yeah, let's just keep moving forward and see if we come across an indirect proof. So now we're going to talk about theorems. Okay, a theorem in logic is an argument that can be proven with no premises at all, right? In other words, it's like a law. It's always valid, regardless of the way the world is, right? It's going to be true no matter what. Okay, we only have a few of these. There's a bunch of theorems you can prove. You can convert any argument, any valid argument, into a theorem. But there are some big ones that we'll talk about. Let's see. First up, the law of excluded middle. P or not P, right? We'll talk about this, and we'll talk about the law of non-contradiction. It's not the case that P and not P, okay? All right, so with a theorem, we don't have any premises, okay? We're still gonna draw a line just for the sake of keeping things consistent, but we don't have any premises. How do we begin if we don't have any premises? We're going to have to run one of those negation introduction or indirect proof strategies. We're going to have to prove indirectly. How do we do that? We assume the opposite of what we want. So I'm going to assume on line 1 the opposite of the law of excluded middle. Okay. This is going to end up being an indirect proof. That's good. So it's not the case that P or not P. Okay. What do I do with this? Right? How do I build from this? I'm gonna have to make another assumption. Okay. This time I'm going to assume P. Let's assume P just to see what happens. Well, now that I have P, again, I'm trying to find a contradiction, right? What I'm doing is trying to generate some kind of contradiction. That's why I assumed P, and that's why I'm going to make the next move here. I know that I can get P or not P from my assumption of P, right? That's just disjunction introduction on line 2. If you know something, or if you assume something like P, you can add anything else you want to it with a disjunction. So why not P? Okay. Now look, lines 1 and 3 are contradictory. Negation, elimination, 1, 3. Now that I've found a contradiction, I can get out of this assumption of P. I know that P must be false, right? It led me to a contradiction. So that's negation introduction, 2 through 4. Okay, How did that help? I got not P. That's not what I'm looking for. Well, it helped because now I can just do the same move again, right? I can add a disjunction plus anything else I want to a line I have. Now that I have not P, I can get P or not P again. Disjunction introduction, line 5 this time. But look, that's a contradiction again between 1 and 6 this time. Now that I've arrived at a contradiction, I'm allowed to say my assumption must have been false. But because my assumption is a negation here, I'm not introducing a new negation. I'm getting rid of it. So this is going to be indirect proof. P or not P, indirect proof 1 through 7. Okay? 1 through 7. Now, remember, we don't have any premises, so there's actually no bar here. Realistically, there's no bar here. Notice that means on line 8, our conclusion, you have no vertical bar. There is no vertical bar at all, which means no assumptions are required. No assumption of premises are required to get you here. Okay. All right, let's end by looking at the last one here, the law of non-contradiction. It's going to be pretty straightforward. We're going to begin again by assuming the opposite of what we want. So we're going to start by assuming P and not P. Okay, well, you can already see we're going to get to a contradiction pretty quickly, right? On line 2, I'm going to break this apart. I'm going to get P by itself from line 1. I'm going to get not P by itself again from line 1. That's a contradiction. Negation, elimination, 3, 2. And if I have a contradiction, then I know that the assumption that led me there must be false. So line 1 has to be false. It's not the case that P and not P, negation, introduction, 1 through 4. Okay, pretty simple. Okay, so that's going to be it for this week. Just work through the problems at the end of chapter 17 for more basic proof strategy practice. Next week, we're going to introduce a few more rules, but they're not meant to make things more complicated. They're meant to simplify things. Okay? They make things much faster. But that's going to be it for now. So I'll see you next week.